This lecture will be the first in a 5-part series on my theory of induction. This first lecture will cover inductive narrative systematization, a method for laying out an inductive proof in its proper order so that you and others can see that proper inductive reasoning has been used properly. This lecture was given in 2024 at the Objectivist Conference in Charlotte, North Carolina. Let's understand the method of systematically laying out an inductive proof here on Inductica. Modern physics is fundamentally flawed. The two theories that form its foundation give correct predictions of the phenomena, but they give a false account of the underlying nature of the phenomena that give rise to those predictions. Quantum mechanics, for example, is a theory that violates the law of identity. It gives us this world where there's particles that are waves at the same time, or particles that are in multiple positions at the same time, cats that are dead alive at the same time. Now, it turns out that modern physicists actually don't really take this seriously anymore. They used to, but they don't take this seriously anymore. But what they're left with is a theory that makes correct predictions, but doesn't give us, but since they've dropped the subjectivism, there's now no longer any interpretation of what the underlying phenomena are. The attitude now is, shut up and calculate. That's literally something that is said, shut up and calculate, and they're serious about that. It makes the correct predictions. Why does it matter that we don't know what's going on under the surface? It's not really a scientific issue. General relativity, on the other hand, is a subjectivist theory. It says that different observers have different realities. So, for example, if we imagine this gentleman here on a moving starship, he's on the starship, so it is stationary with respect to himself. He's going to measure it to be a particular length. This guy, on the other hand, this observer, he sees that the starship is moving with respect to him. He measures it to be shorter. Now, under general relativity, it's vague as to whether this is the reality of the situation, whether it's actually shorter for this guy, or whether that's just a difference of measurement. It's not clear according to the theory. I've forgotten to start my timer. Don't want to go over. Okay. It's unclear according to the theory. Let's see. Now, to understand the nature of this theory a little further, it's kind of hard to understand this because we don't know what's causing this difference in measurement. So I'll give you an example where we do understand the difference in measurement. As you're probably aware, fish do not appear in the actual location they're at. This is because light bends when it goes from water into air. Now, and as a result, different observers will see the fish at different locations. Now, we fully understand this. We fully understand the cause because we understand the math of how exactly the light changes direction. So we're able to account for those differences in observations. Imagine, to understand the place where general relativity puts us, imagine a theory where it tells us what the short guy sees. It tells us what the tall guy sees, but it doesn't tell us why there's a difference. As far as the theory is concerned, well, maybe it is actually different for the two guys. As long as it gets correct predictions, who cares? Now, the solution, as we probably know as objectivists, is to return to the observations. After all, if you have a flawed theory, check your premises. Where should your premises come from? Reality. Go back to the observations. For a field as successful as physics, though, where there's this long chain of prior knowledge, going back to the observations is not enough. Well, actually, it is enough, but it's way harder than it sounds. The reason is that all observations at this high level of physics presuppose some kind of long chain of prior theories required to actually interpret the observations. So let me give you a very simple example. When you stand on one of those old bathroom scales and it gives you your weight, you might think, oh, well, that's a direct observation. That's a direct measurement. It's not direct, though. That measurement relies on a certain assumption about how much a force will deform a spring. So even for a simple measurement like that, there's an actual physical theory that goes into the measurement. And you can only imagine for higher level physics the kinds of theories that go into those measurements. So what's the solution? My particular solution is one of taking no shortcuts. I have written a theory of induction, a theory of proving scientific conclusions from observation. And what I want to do to prove this theory in practice is to use the theory to reprove all of physics from the beginning. I think this is what's required. And what that will allow us to do is to gain certainty of all of the conclusions known so far. Once certainty is gained of all of the conclusions leading up to quantum mechanics and relativity, we will know which prior theories we can rely on to interpret the measurements and which ones we cannot. And what I'm going to give you today is a demonstration of this theory. Specifically the part of the theory that reproves scientific conclusions. Now, before I start, I'm going to make a quick note because it might be a little jarring. The form of my theory is a fictional, the form that my demonstrations of inductive proof take is that of a fictional narrative. What this story I'm about to tell you is going to sound a lot like a history lesson. It's not history. I made this up. This is a fictional character we're about to see. So keep that in mind. Our fictional hero, so we're going into a demonstration of my theory of induction. After this demonstration, I will give you the principles so that you can see which principles were at play in this example. This rather long example I'm going to give you, a story. And it starts with this fictional hero, Salviati. He's a Renaissance Italian physicist. Okay? And Salviati is motivated to understand the nature of air. There's this stuff all around us, apparently. Is it stuff? Is it nothing? It can't be nothing because you can actually feel it like hitting your face. You know it's some kind of thing. But Salviati has a question. Is air a form of matter? Does it have weight? Now, this motivation has given rise to the vacuum pump. I don't have time to explain the workings of the vacuum pump today. That's not our purpose. But let's just say we have vacuum pumps. And what Salviati does to answer his question is he takes this bottle and he weighs it. He just finds the weight of the bottle. He attaches it to his vacuum pump and sucks the air out of it. He then weighs the bottle again. And now it weighs less. Air has mass, or it has weight. So that is what Salviati is able to conclude in this first unit. We're going to have 3 units, 3 inductions. In the next unit, we have a different motivation that starts our scientific journey. We want to understand this process of suction. So what's suction? Once the vacuum pump was invented, there were these industrial processes that used, Dom's is laughing. So we got these industrial processes that use suction. How does that work? So for example, when people want to pull water out of a well, they pump the air out of this tube. That brings the water up, so we don't have to lower a bucket down in there and get the water. Other applications would be pumping out the inside of a mine so that people can actually go down there and dig for ore without swimming. So this leads Salviati to a certain question. Something that people found in these industrial processes is that no matter how good you make the pump, you can actually never lift water further than 10.4 meters. So that's kind of weird. You'd think the better the pump, you could start lifting it past here, and you could get it higher, but you could never break this limit. So Salviati asks, why can suction only lift water 10.4 meters? Investigation. Salviati starts this investigation by asking, well, why does suction even lift the water to begin with? How does that work? Now, what he's heard a lot of people say is that nature abhors a vacuum, okay? So, all right, now let me tell you, there's a lot of problems with this formulation. I'm going to skip those. I'm going to tell you about one aspect of my theory of induction here. This is not what I'm focusing on today, but it's part of my theory of induction. When you give an account of causes, it's better to identify entities, their properties, and how they act, instead of general rules like nature abhors a vacuum. Again, there's problems with nature abhors a vacuum. There's nothing wrong with general rules as such, but what is much more desirable is to identify the entities, the actions, and the properties that give rise to those actions. So Salviati says, what can I figure that out? So he has another thought. He says, okay, well, there's a vacuum right here, and maybe the vacuum is sucking the water up. So nothing, the vacuum is sucking. Well, that violates another aspect of my theory of induction, which is that nothing isn't a thing. I didn't originate that, but it is part. Parmenides. Nothing isn't a thing. This ends up being a deep fact, even though you can state it so colloquially. So that doesn't make sense as a cause. So after a few weeks of meditating on this, he has an idea. He says, I already know air has weight. So maybe the weight of the air, this big column of air above us, is pushing down on the water, and then that makes the water squirt up, okay? Because it's got nowhere else to go. It squirts like this. Now, normally, there's a bunch of air in the way here, but if you suck the air out, it's not in the way anymore, and so the water is able to get pushed up. So Salviati entertains another question to investigate this further, question 2 of Unit 2. Salviati asks, can this effect hold up some kind of consistent weight? Okay, it held up 10.4 meters of water, but maybe because there's a certain amount of air, it can only push a certain amount of weight up. So can I confirm that it can only push up a certain amount of weight? He comes up with the following investigation. He knows that mercury is 13.56 times denser than water. Okay, mercury is denser than water. So he takes 10.4, he divides it by 13.56. He comes up with 76.7 centimeters. So if this hypothesis is right, that it can hold up a certain amount of weight, then it should only be able to hold up 76.7 centimeters of this denser fluid, mercury. So he takes a test tube, fills it with mercury, and then puts his thumb over the top, making sure there's no air pocket in there. Turns it upside down, puts it in a bath of mercury. He wasn't aware of mercury poisoning. Then he takes his thumb off, and common sense would tell you that the mercury would just kind of like flow down. And it does, but only a little bit, only down to 76.7 centimeters, just as expected. Now, you might be tempted to think that he has proven his conclusion. He's proven that, yeah, the air is above us, it's pushing down, and it causes this thing. It pushed up a consistent amount of weight, right? That's not really how it works. In science, it's not enough, according to my theory of induction at least, it's not enough to just say, oh, well, I found an observation that's consistent with my hypothesis, so I guess I can go home, I did it. No. What you have to do, and we're going to see how this works, what you have to do instead is make certain observations that allow you to reason to a new conclusion with certainty. Not just, oh, it was consistent. No, you have to see observations that make it certain that your hypothesis is correct. And this leads Salviati to his next question. Is this effect really caused by the weight of air above? That leads him to another investigation. What he does is he takes his apparatus. In the modern day, we call this a barometer, by the way, in case it looks familiar. He seals the apparatus off from the outside world. He doesn't suck the air out. There's still air in there. But the idea is that it's in a box. The box is sealed, so the pressure from the column of air above can't get in. Okay, so you're isolating it from the big stack of air. So Salviati thinks if I isolate it from the big stack, and if I'm right, then the mercury should fall. It doesn't. Okay, it's not looking good, right? It's not looking good for his hypothesis. Okay, Salviati comes up with a different hypothesis, and this is question 4. In my view, a hypothesis is really a form of a question. It's a kind of question. Salviati's hypothesis is, what if the air inside is already compressed? Okay, so what do we mean? So maybe, he says, air compresses like a spring. So that stack of air above compresses the air down here at the surface of the Earth, crushes it, that's the sound it makes, and then crushes it, and then once it's crushed, it kind of like pushes out with the same amount of force that is applied to it. So here we have each little bit of air pushing out on its friends in each direction. Now, the way Salviati came up with this idea is he realized, well, before we pump the air out, there's air trapped in here. Before we pump the air out, this air is actually able to keep the water at bay, okay? So it's isolated from all the air above. So maybe air pushes out with this pressure, right? Maybe air just pushes out because it's already compressed. So that's his hypothesis. Note that the hypothesis came only with, it was only possible based on his prior reasoning. All of this is a chain, as we're about to find later. Salviati thinks of another investigation to test this hypothesis. So the new question is, Salviati comes up with a new investigation. He takes this, he pumps the air out of the inside. And once he does, the mercury level goes down, and he didn't plan ahead. He wasted a bunch of valuable mercury, okay? So the air's doing something. The air in here is responsible for the downward force. So you see, like, let's take note of this. There's a difference between seeing some observation that's consistent with your hypothesis and seeing an observation that allows you to reason to the conclusion with certainty. Salviati got the air out of the chamber, and then the effect went away. There's no other possibility other than the air somehow, he's not sure why yet, but the air is pushing down on the chamber. Is it pushing through the test tube? Like, there's no evidence it could do that. Is it conveying a force magically like through the test? It does, yeah. No, there's no other known ways that things can act that could explain this phenomenon. Salviati is able to come to the conclusion that air pushes down on fluids with enough pressure to hold up 10.4 meters of water. Notice he's been able to come to a conclusion about the force. He hasn't yet come to a conclusion about the actual pushing out hypothesis, the springy air hypothesis. So that's what he's going to investigate next, motivation. This is Unit 3. He wants to understand the nature of air and how it pushes on fluids. And so he's going to test he's going to investigate this question now. Is it true that the air actually gets compressed and pushes outward like a spring? To test that, or rather, test is the wrong word because test kind of makes it sound like he's going to, test the hypothesis. He's going to conduct a certain observation that makes the hypothesis, that makes it possible to prove the hypothesis. That's really a better way to think of it. He takes this J-shaped tube. He pours some mercury in there. Then he caps this side of the tube off and pours additional mercury in. Okay, now notice what's going on here. The mercury level went up. This was this little line. If you can see the microscopic line here, then this was the prior height of the mercury. It went up. That means that the air pocket here got compressed. It's smaller than it was before. And we also see evidence, well, conclusive evidence, not just, evidence for, but we see with certainty that this pocket of air is producing a force that's large enough to hold up this weight of mercury. The air is producing more force than it was before. How do we know? Let's go into more detail there. Ordinarily, the mercury would have equilibrated. It would have, if you kept pouring it in here, it would have like that over the top like this. But it was held at bay. How much was held at bay? That much was held at bay. Okay, so he knows that the air is producing this much force, a force equal to whatever height of mercury this is right here. And so he's able to conclude that when you crush air, it pushes out with a greater pressure. And this leads him to a further overall conclusion, tying everything from this example together. Number one, air has weight. Number two, air is compressed by the air above because it has weight, so the air above comes down, crushes the air down here. Number three, compressed air pushes out like a spring. Number four, this compression pushes the water down. So each of these little bits of air is pushing out, including down, pushes down on this water, which pushes the water up. And so he has identified the cause of suction. Notice how it's in quotes now because we shouldn't even call it that now that we understand its cause. Now, Salviati was able to achieve certainty by following a very particular method. And I'll tell you about that method now. The purpose of this method is to prove conclusions to yourself. So if you lay your own reasoning steps out in a story like this, you have to obey certain principles, which I'll tell you about. If you lay your observations and reasoning steps out in a certain order like this, it allows you to prove your conclusions to yourself. By transmitting that story to others, it allows them to see that as long as you are honest about your observations, the conclusion follows from the observations and the reasoning steps. In order to, now, it's important to note, relate this to the rest of objectivism. In objectivism, the gold standard for proof is reduction. You take your abstract ideas and then you identify the observations that gave rise to them. This is a good process, but in a long chain of evidence like that in physics, it's really long. It's really long by the time you get to quantum mechanics and relativity. Going backwards isn't really practical. This method goes forward. This method starts with observations and goes forward. So it's like reduction, but just in the opposite direction. And this method follows certain principles, which I'll now tell you. So all of these principles were implicit in the example, and I'll be referring back to the example constantly. The primary principle is logical order. You must not make assumptions at any point of the process. You must reason only from ideas which have been proven earlier in the narrative. And when you use those ideas, you cite them to show that there was an actual proof at one point. That's what I just said. So, for example, Salviati reasoned from knowledge that air has weight. The way he came up with this hypothesis that the air was pushing down and therefore pushing the water up here is because he came up with that he proved that air has weight. So that hypothesis came from prior knowledge. Now, here's something that isn't so obvious. Observations also depend on prior knowledge. You might think that a picture like this might speak for itself, or you might think in general, like observations are primary. You look, there's evidence, and then you interpret the evidence, like the observations are the ground level. But that's not really true. A complex observation like this, an experiment, a deliberately contrived setup to interrogate nature, relies on prior knowledge. Salviati only thought of this particular experiment. Again, this is the experiment where he puts the mercury contraption inside a box and then he doesn't vacuum the air out. He does this because of his hypothesis, because of prior knowledge that gave him evidence that the air above was pressing down on everything, and so he thought, I need to seal it off. This observation relied on prior knowledge. And so in an inductive proof, you can't just suddenly come up with an idea like this. You can't just, and then Salviati smoked some weed, and then he thought of this. If you've ever been in a science class, you probably kind of had this idea before. It's like, well, where did they come up with all of this? Were they gods? Were they insane and then just got lucky? It's not clear. And none of them were gods. None of them were insane. They were just they just understood the prior knowledge and reasoned from it. Now, for probably a lot of you are kind of wondering, like, why is it a fiction? That's a little weird. The reason it's a fiction is because the process of proof needs to be essentialized. Okay, so if you're reproving historical inductions, then what you need to do is you need to cut out all of the wrong turns and false starts and like reasoning steps that are way too complicated. Shave it down to just the minimum number of observations and reasoning steps required to prove the conclusion. Now, you need to include only observations which were literally done, or maybe you can make your own observations and add them to the history, but you need to be confident of the observations. But once you've done that, it's now essentialized. Because this isn't the actual history, you should not use the actual names. You should just make up a name. You can ask me where I got the Salviati's name from the question period. Probably a lot of you know. Oh, another thing. If you're a scientist and you come up with your own, and you make your own discovery, you should systematize your own discovery process in this same fictionalized way. Again, making sure you actually did the actual observations, but you can arrange those observations and reasoning steps in any order you want, because you could have done that, and it would have been valid logic. A narrative also gives us certain advantages in holding the proof and adhering to the proper standards of inductive method. One of these advantages is characterization. Your character is a person, a fictional person, but we have a certain knack for like understanding other people, and we can leverage this to understand what Salviati knows and what he doesn't know. We watch him on this journey of discovery as he grows in his knowledge, as he learns this thing and that thing. And this allows you, this intuitive sense we have for understanding other people and what they know and what they don't know. This gives us the ability to call BS on bad inductive logic. So for example, if Salviati were to just come up with some new experiment that didn't follow from what he knew before, you'd recognize that as a plot hole, basically. And that brings us to the next aspect of story that helps us with scientific proof, and that's the issue of plot. A plot is a series of logically connected events. And we saw that here. Salviati learned that air has weight. That allowed him to come up with this hypothesis. That allowed him to test that hypothesis by seeing if he could stop the weight from pressing down. That led him to his new hypothesis about the air getting compressed and pushing out like a spring. There's a logical order to it. And for those who haven't watched too many Marvel movies, we're able to find when that logical order is violated with a plot hole, with Salviati coming up with something he didn't have the ability to actually think of. Now, without logical order, without presenting science in a logical order with all of the inductive prerequisites, science classes can often be dogmatic even when they give the observations. So they might give you a picture like this. They'll tell you it's a barometer. They'll tell you the height represents the pressure somehow. But why does the height represent the pressure? How do I know this is giving me anything that has to do? It's just freaking a tube. It's just a tube with fluid in it. And here's another thing to think of. Do you even understand what pressure is? Without all this context of the air must be crushing, or the air must be getting crushed like a spring. Do you even understand what pressure is without that prior knowledge? So they just tell you pressure, here it is, good luck. That's how science felt to me, my whole schooling. Good luck in trying to understand this. Another principle of this narrative is that our narratives should proceed in a particular set of phases: motivation, question, investigation, conclusion. Let's talk about the motivation phase. Motivation must be included as a matter of proper scientific method. Knowledge is not an end in itself. The only purpose of knowledge is to give us power over nature and to help us live better lives. As a result, any scientific investigation must be shown, there must be some argument for why it will help us somehow. All scientific enterprises are guilty until proven motivated. This is a standard they must, this is a standard they must adhere to. Now, this standard does not confine us only to scientific investigations that yield some kind of immediate profit. Francis Bacon taught us that knowledge is power. So we know, generally speaking, that knowledge of the world, fundamental knowledge of the world around us, will end up being useful at some point. So for example, even though there was no particular immediate application of it, finding out the basic nature of air is valuable. There needs to be an argument like this, at least like this, at the beginning of an investigation to show that what you're doing means anything. But not only that, the motivation actually constitutes part of the prior knowledge that we are reasoning from in an induction. So imagine if Salviati were to, imagine you didn't know any of this story, you didn't know any physics, let's say, and Salviati comes up to you and he says, I got this idea. Maybe air is getting pushed down and it gets compressed like a spring and then it pushes out. You'd be able to understand what he's talking about. You have the prior knowledge required to understand the claim, but you do not have the prior motivation to entertain the claim. You would just say, like, cool story, bro, but like there's a million other hypotheses out there. There's just, like, why should we investigate this one? Why? Well, Salviati had a bunch of prior evidence for why this hypothesis was worth entertaining. And so for this reason, the motivation must be included as part of the issue of logical order. Motivation is part of inductive logic because motivation is what justifies the question. Questions frame an investigation in terms of prior knowledge. It's not just, they form a very important part of the process. And as a result, because they're framed in terms of prior knowledge, we got to make sure it actually follows from proven prior knowledge. So for example, Salviati's hypothesis, which again, a hypothesis is a kind of question, his hypothesis that a certain amount of mercury would be held up had to be justified by the prior evidence coming from the amount of water that was being held up. So questions must be justified with prior knowledge because the right question can lead to a fruitful result, and the wrong question can lead us in circles. For example, the alchemists investigated the question, can we turn lead into gold? There was no evidence at the time that such a thing would ever be possible. A different question they could, so that question, which was unjustified, unmotivated by the prior evidence, led them in circles. The better question that chemists ended up asking was a more general one. They asked, can we create valuable materials out of less valuable materials using processes of chemical change? And of course, they succeeded at this in spades. One example is aluminum, which you may be surprised to know was once more valuable than gold. And now we use it as a disposable tray. That's how cheap it is. So the dream of the alchemist was achieved in principle, maybe not specifically, but generally speaking, it was achieved by asking the right question. So questions must be justified. And it turns out that for many scientific investigations, formulating the question properly is actually the hard part. Often, once you get clear on what question you're actually supposed to ask, the answer just becomes completely trivial. So we need an aspect of the scientific method, the inductive method. We need an explicit aspect of the inductive method that teaches us how to formulate proper questions. And part of what I'm presenting here is that questions must follow from the prior knowledge that has been proven. That leads us to the investigation phase. And this is pretty straightforward. You got to present the observations and reasoning steps that led to your new conclusion. So you saw a bunch of examples of that. Now, the particulars of the reasoning steps, I actually didn't go into. All I did was kind of I only gave you about 20% of my method of induction here. This is just the way of structuring your argument. And you can see from the story that it kind of felt intuitive that it was all proven. But really, you have to cite particular methods of inductive reasoning to show that you adhered to proper methods of inductive reasoning. And the rest of those steps of inductive reasoning can be found in my book, which an early version of that is available on Patreon. So patreon.com/Inductica. So if you support my YouTube channel, you can get a copy of the book. And of course, in the conclusion phase, you got to end with a clear proposition, stating your conclusion, which can be cited in further inductions. So that is the MQIC narrative inductive method. I'll summarize. Proceed in a logical order. Don't make any assumptions. Reason only from conclusion established earlier. Present your process of discovery in an essentialized fictional narrative. Cite prior conclusions and the method of induction in order to justify your observations and reasoning steps. Proceed in the order of motivation, question, investigation, and conclusion in order to maintain that logical order. That's the purpose of this, is to keep you in bounds and not make assumptions. Again, the purpose of this is to prove conclusions to yourself. Once you have it written out and you see that you followed the correct methods of induction, you can see for yourself that you are right, and you can transmit that proof to others. Now, what my ambition is that this system of narrative, in combination with the rest of my principles of induction, which I didn't have time for, my ambition is that this will systematize the process of scientific proof. So imagine a world where scientists had this common frame of reference, this common standard, where they could prove to themselves, yes, I know I'm right now, and they could transmit that certainty to others. Imagine a world where the proper method of induction is understood with the same kind of certainty and clarity that deduction is understood with today. I think that is a fundamentally different world than we live in now. I think that's a world where humanity has taken a fundamentally new step forward. Questions? Yakir. Yeah.
Okay, I have some.
Oh, well, hold on. You gotta have the mic, or else the recording won't pick you up.
I have several questions. The first, you started by saying that the theory of relativity and are not proven.
They're wrong.
What? You said that they are wrong. The Einstein and Heisenberg follow exactly the path that you did here.
I disagree.
Why do you disagree?
There's a lot to it, but in short, they followed the hypothetico-deductive method. They had what that means is they saw the phenomena, they came up with a hypothesis for why those phenomena were the way they were. They came up with a hypothesis that recapitulated the results. Then they made some tests and found that those tests were consistent with the hypothesis. That's not enough to prove something. And the fact that these theories violate basic philosophic axioms that we understand shows that they have to be wrong, but even a wrong theory you can still guess and check your way into a consistent theory even with false conclusions.
That's not the way they did it. Einstein did a theory of, he found a light and the energy and his energy equation, not by, he did it by a very scientific method. It's not an inductive method, and I have a problem with you using induction induction is defined in mathematics as a specific method of proving stuff.
Yeah, there's a different definition of induction, but also I'll just sustain your objection for now, and we can talk more after the questions. Who else? Luke. Luke.
Am I on?
Yes.
I know nothing of physics, so this is not quite a physics question. It's I'm fascinated by your idea of fictionalizing a proof. My question is, have you applied this for yourself to other things besides physics, like proving other things to yourself?
Oh, no. Here's why. This is hard. Well, that's not quite the right way to say it. This method is very powerful, but it's unwieldy. It's slow. You have to you have to literally start at the beginning and you have to follow it step by step. So trying to prove some other thing in your life, yeah, you could do it, but that would be its own project. What kind of thing did you have in mind for proving?
I don't know if.
Yeah,
like,
so much of what we know relies on this big story that comes before, and you could do it. I just don't have that many lifetimes, so that's really,
no, just something simple like, I think my parents. I believe my parents are taking my money from me. I don't know. Or,
right,
you know
yeah.
what? This is the perfect girl
Okay.
for my life. So how do I? Can I fictionalize that proof?
I haven't thought of this, but that's a great idea. It's worth thinking about. You're looking at me like, how did you not think of that? That's a great idea. Yeah. We got another.
How would inductive reasoning handle things that we can't directly observe or interact with easily, so like black holes or quantum particles and stuff like that?
Ultimately, all scientific proof is based on observation, but we make inferences about things we can't see all the time. So, for example, let's think of something Salviati. Salviati did not literally feel the air pressure, right? He inferred it by looking at its effects. So with something like a black hole where direct observation might be difficult, you observe what you can and then make inferences about that which is hidden. And part 4 of my theory actually gives a bunch of rules of inference. I use the word inference to specifically mean a deduction from what is observed to what is not observed. I have like a specific way of inference. Other people use it in other ways, but I mean that specifically. Deducing from what is observed to what is not observed, and that's very important in science. Who else? Oh, Cynthia, tell me when I have 1 minute. Yeah. 1 minute?
So you mentioned how like creating the hypothesis and then finding an observation essentially that matches the hypothesis is not sufficient.
Yeah.
What's the additional component you're presenting here? Like what is the sufficient?
Yeah,
set
it's hard to
have a
see
proof?
it because we were all trained to think scientifically that way. So when you see the parts of the narrative, you're thinking like, oh yeah, that's consistent with the hypothesis. No, you don't want to. You want to get that mindset out. You want to ask yourself specifically, I know some stuff from before. I'm seeing some more stuff. Can I reason like deductively? This is the part of induction that involves deduction. They're not mutually exclusive. Can I reason from what I know before and from what I see right now to a new conclusion? So for example, in the case of the mercury, let's see if I can find it quickly. The mercury in the J tube, that's way far back. Oh well. The mercury in the J tube is getting compressed, right? You can see it getting compressed. The mercury in the J tube is holding up more mercury than it was before. So you're making an inference from what you're seeing. You're not saying, oh, it's consistent with my hypothesis. You could say that in that situation, but that's not the right method. The right method is instead to say, I can see that it's holding up more mercury, so it must be pushing with a force equal to the weight of that mercury.
See, I think you're getting at the problem where a certain set of observations is consistent with multiple theories, right? And traditionally,
What other theory is it consistent with?
To take an exaggerated example, the invisible green gremlins pushing the mercury.
There's
right?
no prior evidence for such a theory.
Right.
So
That's
my
the principle of
theory
parsimony,
rules out. It's
which
not
is-
parsimony. It's that it's not like, oh, we need to like have less assumptions. That I don't see that. It's that your assumptions need a basis in prior evidence. That's part of that's part of the theory. I didn't really go into that, but that's part of my view.
If you're going based on prior theory, it sounds like you can get into a kind of an echo chamber kind of effect at some point if you don't I mean, this gets to Feyerabend's point of, given a particular train of thought, it can become, as his words, boorish over time, and stale, and now no one can get out of the trap because, well, it's not part of prior theory. But you might need something completely, utterly tangential to break a stalemate. How do you handle that?
I'm not sure if, so you're saying a lot of times these stalemates are caused by faulty prior premises, and the way my method handles that is to say you have to prove your prior premises before you start reasoning from them, and you have to lay them all out on the table first. You can't be reasoning. The history of science has a lot of instances where people are reasoning from unproven prior premises. It's like, here's an example we laugh at today, but like the Greek astronomers took it seriously. They would say, the circle is the most perfect shape. Why? I don't particularly like circles, by the way, but that's what they thought. The circle's the most perfect shape, so obviously the planets are going to move in a circle because like the heavens are perfect because they're like up. I mean, I'm mocking them a little bit, but like, they didn't think those assumptions through. So the way I deal with this is to check prior assumptions. That's the main way. So in closing, I want to tell you something else about what drives me here. It's not just a lust for discovery. At the heart of this quest is actually a moral mission. I want to show people that you can grasp reality for yourself with your own mind. We know as objectivists that the cause of our moral and political degradation is fundamentally that we've lost faith in reason. We've lost our we've lost our confidence in reason. We have skepticism about whether reason can actually know reality or not. What I want to show with this method of induction is that certainty is possible, that we can reason from observations to new conclusions, overturn a century of bad thinking, and show that we live in a rational, fully real universe. So if you want to be a part of that quest, then you can watch my YouTube videos here at this URL, and you can support the project at patreon.com/Inductica. And we actually have a few supporters here. You can raise your hands if you want to be known. Yeah, so thank you very much. And in closing, reproving physics is going to be a tall mountain to climb. But to stand on the shoulders of giants, there are no shortcuts. You must earn every handhold yourself. And I think the view at the top will be worth it. Thank you.
Thank you very much, James. Excellent.